Welcome friends. Hope you are all well, good. Today we shall discuss about the conservations of linear momentum and the impulse or impulsive force. The basic theory of conservations of linear momentum. What is the linear momentum? Linear momentum is mass into velocity. The product of mass into velocity is equal to linear momentum. So, if m is the mass of the particle and v is the velocity in any particular direction, the linear momentum p is equal to m times v. The product of mass and velocity is equal to linear momentum. Now, what is the conservations of linear momentum? If any external force is absent on the particle, then the linear momentum must be conserved according to Newton's second law of motions. So, if we can write from the second motions of Newton's law, F is equal to m times a, F equal to m times a, or F is equal to m, a means dv dt. If this is the vectors, F is equal to m dv dt or ddt of mv. mv means dp dt, where p equal to mv is the linear momentum of the particle. The relation with force and linear momentum is force is rate of change of equal to rate of change of linear momentum. Force is the rate of change of linear momentum. If no external force were present for such explosion of a bomb of mass m initially as rates explodes into two fragments of mass m1 and m2 with velocity v1 and v2. In this case, the external force is absent because when a bomb explodes, the internal force were present because due to some chemical reactions or thrust force, it becomes splitted into two elements. But as external force, it does not occur any external force. So, from here we cannot write F is equal to ma. So, to solve this type of problem, we must be surrendered to the conservations of linear momentum equations, where F is equal to ma, force is not possible to apply. Where F is equal to ma apply? If there are any external force were absent, suppose pulling a particle, pulling a car, pushing a trolley, then external force were absent, present. But if external force were absent, then the relation F is equal to ma is meaningless. In such cases, if we get F from this equation, if we get F is equal to 0, what can we get? If F is equal to 0, then dp dt is also is 0. That means P is equal to constant. So, from this we can get that if the external force is absent, their momentum must be conserved, which is occurred for this problem. Now, is this only possible for a single particle problem? No, this is also possible for a system of particles. For a system of particles, if there are so many particles of masses m1, m2, m3, m4 and so on, and force applied on each particle is external force is 0. That is, if F1 is equal to 0, the force on M2, F2 equal to 0, force on M3, F3 equal to 0, force on M4, F4 equal to 0. Therefore, the momentum of individual particle, that is P1 plus P2 plus P3, and for nth number of force Pn, must be conserved according to the conservation of linear momentum. Must be conserved according to linear momentum. So, this can also be true for center of mass problem, which we shall discuss later. So, what we get from this relation, that if the external force is absent, then the linear momentum of the particle must be a conserved quantity. This is the basic law of conservation of linear momentum. Now, for example, we take this problem. Suppose this is a bomb. This is a bomb. We enlightened bomb in Durga Puja, Kali Puja festival. Suppose this is a bomb. It initially at rest, that is V equal to 0. Initially at rest. Due to some chemical reaction, it explodes into two fragments of masses m1 and m2. It can be exploded into two particles. Now, the velocity of m1 fragments is v1 after explosion, and velocity of m2 particle is v2. Now, the question arises that in which direction the particle will go, the fragments will go. What is the relation between their path? Is they go along the same direction or perpendicular direction or opposite direction? That is the angle between them is 0 degree, 90 degree or 180 degree. We does not solve it. We cannot solve it from F is equal to MA relation. Why? Because here external force F is equal to 0. So, how can we use the equation F is equal to MA? This is the most important relation and important mathematics of conservation of linear momentum. Now, for this problem, how we can solve it? So, as the particle initially has rest, so the product of its mass m and velocity v must be equal to product of m1 v1 plus m2 v2 according to law of conservation of linear momentum. Now, v is 0. We can say the particle or bomb is at rest. Then the value of mb could be 0 for, so m1 v1 plus m2 v2. Therefore, m1 v1 is equal to minus m2 v2. m1 v1 is equal to minus of m2 v2. Or v1 equal to, or v1 by v2 equal to minus of m2 by m1. v1 by v2 is equal to minus m2 by m1. What is the significance of this equation? So, we can get, I can write it, so you can watch it clearly. v1 upon v2 is equal to minus of m2 upon m1. That is, the velocity is inversely proportional to mass. That is, the lighter element will go with more velocity and the heavy element will go with less velocity. In which direction? The negative sign implies that it goes into reverse or opposite direction along the same line of path. This is the beauty of conservations of linear momentum. Now, if someone asks what is the speed of this particle, we know the magnitude of velocity gives the speed. That is, magnitude of v1 by v2 is equal to m2 by m1. Therefore, speed of particle is also inversely proportional to the mass. This is the law of conservation of linear momentum. Let us take an example. Now, before we start problems, we can also know the relation of between the linear momentum and kinetic energy. P is equal to mv. P is equal to mv. Now, if we square both sides, P square is equal to m square v square. If we arrange it in this manner, 2m into half m v square, the value remains m square v square in this side. 2 cancel and m square v square. Now, p square, the square of linear momentum is equal to 2mk, or k, kinetic energy, equal to p square by twice m. Kinetic energy is equal to p square by twice m. This is the relation between the kinetic energy and linear momentum, k equal to p square by twice m. Now, we can solve a problem through these equations. How can we solve? If linear momentum is increased by 100%, B 1%, find percentage increase in kinetic energy. This is the mathematics. If linear momentum is increased by 100% by 1%, then find the percentage increase in kinetic energy. How can we solve it? For problem A, we can know kinetic energy K is equal to P square by 2m. Equation number 1. Kinetic energy K is equal to P square by 2m. Now, if the kinetic and if the momentum is increased by 100%, what will be the momentum in the second case? Let us consider the second case. The momentum becomes P1, that is P plus P into 100%, 100 by 100, that is twice P. P1 is equal to 2P. Therefore, what is the kinetic energy when the linear momentum increase by 100%, K1 equal to P1 square by twice M. P1 square by twice M. Putting the value of P, we can get 2P square by twice M. That is 4P square by twice M. 4P square by twice M. Now, percentage increase in kinetic energy. How can we find it? Therefore, percentage increase in kinetic energy is final kinetic energy minus initial kinetic energy by initial kinetic energy into 100%. This is the percentage change in kinetic energy. Initial final value minus initial value divided by initial value. Final value minus initial value divided by initial value into 100% is the percentage change of an physical quantity. Therefore, K1 means 4P square by 2M minus K means P square by twice M divided by K, that is P square upon twice M into 100%. Into 100%. If we get this, what is the value? What is the value we get? That is, if P square by, we can take P square by twice M is equal to K from the relation. K is equal to P square by 2M relation. Then we can get percentage change in delta K percent is equal to 4P square by 2M means 4K minus P square by 2M means K by K into 100%. That is 4K minus K, 3K upon K into 100%, nearly equal to 300%. So, we can show that if linear momentum is increased by 100%, then kinetic energy must be increased by 300%. Now, for small value change of linear momentum, what we can get? We can get the percentage value of 1%. If in the second question we can say if P is changed, linear momentum is changed by 1%, then what is the change in percentage of kinetic energy? For small value change, we cannot derive in this formula. We can derive with a magical tricks. We can know the relation between P and K is K equal to P square by twice M. K equal to P square by twice M. Therefore, K is proportional to P square. Here the power of K is 1 and power of P is 2. Power of K is 1 and power of P is 2. So we can write 1 percentage change in K equal to 2 percentage change in P. This is the magical tricks. The power of K is 1 percentage change in K equal to 2 power of P, 2 percentage change in P. So 1 means 1 percentage in K, therefore we can write the percentage change in K equal to 2 into percentage, what percent change P? 1%. Therefore 1. That is the percentage change in K is 2%. Percentage change in K is 2%. In this way, we can get the value of percentage change in K and vice versa. So, we can get from this relation. Let us take another example. two blocks A and B. A is mass 1 kg, B is of mass 2 kg, are connected by a string. Now, if we stretch the string, and this is placed on a frictionless horizontal table, on a horizontal table. If we stretch it, then release. Then if we stretch it in this direction and this direction, then release, then find the ratio of magnitude of velocity, find the ratio of speed ratio of linear momentum and kinetic energy. These three quantity should be find out. So, from the conservations of linear momentum, we can solve it. How? How we can solve it? Now, as these are raised initially on a frictionless horizontal table, then must be external force is 0. Therefore, P1 plus P2 must be 0 for 1. P1 plus P2 is equal to 0. P1 is the linear momentum of 1 kg mass and P2 is the linear momentum of 2 kg mass. So, net force on the two blocks are 0. So, as they initially rest, therefore, from the conservations of momentum we can get P1 plus P2 is equal to 0. Then putting the value of P1, what is P1? M1 V1. V1 is the velocity of 1 kg mass plus M2 V2 is equal to 0. And P1 plus P2 is equal to 0. Therefore, from this equation we can get P1 is equal to minus P2. P1 equal to minus P2. M1 V1 plus M2 V2 equal to 0. What is the value of M1? 1 kg. 1 into V1 is equal to minus M2 V2. Minus means minus 2 into V2. That is V1 by V2. V1 by V2 is equal to minus 2 by 1. V1 by V2 is equal to minus 2 by 1. Now we know we can find out the ratio of the speed. So we can know that magnitude of the velocity is the ratio. If we get the magnitude, then negative we removed, that is 2 by 1 equal to 2. Therefore, the ratio of velocity is 2:1. But ratio of speed, sorry, velocity not, speed is 2:1. And what is the ratio of the linear momentum? We can always get P1 equal to minus P2, that is P1 by P2 mod of P1 P2 is equal to 1. That is ratio of the linear momentum is also 1:1. Now, what is the ratio of kinetic energy? For kinetic energy, we can get K. For kinetic energy, we can get K is equal to P square by twice M. That is, K is directly proportional to P square and K is inversely proportional to mass of the block. So, if we get, that is, K1 is the kinetic energy of the first block and K2 is the kinetic energy of the second block, then we can write K1 by K2 is equal to P1 by P2 square into m2 by m1. As p1 by p2, p1 is directly proportional and m is inversely proportional, so you can get k1 by k2 is equal to p1 by p2 that square whole square and m2 by m1. p1, what is the value of p1 by p2 square? p1 by p2 is equal to 1, that is 1 square. And what is the value of m2 by m1? We can get m2 is equal to 2 kg and m1 is equal to 1 kg. That is the value of 2 upon 1. So the ratio of kinetic energy is 2:1. The ratio of kinetic energy is we get 2:1. In this way, we can solve numericals using conservations of linear momentum. Next day, we can show some more critical questions using conservations of linear momentum and impulse, concept of impulse and force. Thank you.